Hello, everyone. My name is Amanda Haller with Audio Precision, an Axiometric Solutions brand, and today we are featuring the Big Six audio measurements. Today we have Ben Collada and David Pennington as our presenters from Axiometric Solutions. Before we begin, I wanted to cover a few housekeeping items. A copy of today's slide deck is available through the handouts section on your screen. If you have any questions during the webinar, you can submit them through the questions section on your screen. We will try to answer these questions during the webcast, but if we run out of time or a longer explanation is required, you will be followed up with after the webinar via email. Without further ado, I would like to pass it over to Ben to get us started.
Thanks, Amanda. Good morning, good afternoon, good evening. Welcome to the webinar. I hope your day is going well so far. Today we will be discussing the Big Six audio measurements. My name is Ben, and today's webinar will be presented by myself and my colleague David Pennington. David and I are support engineers for Audio Precision and GRASS Acoustics, and we work from the AP headquarters here in the beautiful Pacific Northwest near Portland, Oregon. As members of the Global Tech Support Group, we help customers around the world select and use their measurement equipment in a diverse number of test applications. If for any reason you would like to contact us after this webinar, please feel free to use the email addresses shown here. Audio Precision and GRASS Acoustics are part of the Axiometric Solutions Group, which is owned by Battery Ventures. Battery Ventures is a global investment firm with 38 years of experience in more than 400 investments. Our three brands, Audio Precision, GRASS Acoustics, and IMC Test and Measurement, equip engineers, technicians, and researchers with tools such as electronic audio and electroacoustic test instrumentation, high precision microphones, and productive test and measurement systems. We are a global platform with headquarters, sales partners, and representation in over 35 countries around the world. Today, we are discussing the Big Six audio measurements. While there are hundreds of audio measurements that are appropriate for any number of devices, there are 6 basic measurements that are relevant to nearly all of them. This list of measurements includes level, frequency response, signal to noise ratio, total harmonic distortion plus noise, phase, and crosstalk. We will be defining each of these measurements as well as overviewing some common applications and example measurements along the way. Before we discuss these measurements, it's important to understand some basic attributes of sound. Sound is produced by the vibration of an object, creating pressure fluctuations in the surrounding medium, usually air. These fluctuations create compressions and rarefactions of air molecules, leading to alternating high and low pressure regions that propagate through the air and are interpreted by the human ear as sound. There are 2 primary components to sound: the level, or sound pressure level, which denotes the amount of pressure variation in the air, and the frequency at which these variations occur, typically expressed in hertz. These pressure variations can be represented in an audio device by any signal with positive and negative values that are analogous to the pressure fluctuations in the air. A positive value indicates an area of increased pressure, and a negative value indicates an area of decreased pressure, or rarefaction. Electrically, say in an audio amplifier, sound is typically represented by continuous voltage fluctuations in a circuit. This is what is referred to as an analog signal, a signal that is electrically analogous to sound pressure in the air. The voltage does not make any perceptible sound until it's connected to a speaker or other transducer, which converts the fluctuations in electrical energy back into vibration and sound. Digitally, sound is represented by bits in memory or on a hard disk, for example, as samples in a .wav file. The reasons for measuring rather than simply listening to a device such as a pair of headphones are varied. And being in support, we've certainly encountered some interesting applications. One reason is simply that not all devices can be listened to. As I just mentioned, an audio amplifier produces an electrical output rather than an acoustic output and must therefore be measured electrically. However, even in cases where a device can be listened to, a key advantage of making measurements is that the results are objective and repeatable. This eliminates major inconsistencies that can occur when the opinions and preferences of a human listener enter the equation. I've personally worked with, just as an example, with multiple refurbishment centers who sought to replace their subjective listening tests with measurements and audio analyzers for this exact reason. Other common reasons to measure include to evaluate and debug the design of components within a product. For example, the DAC or digital to analog converter and amplifiers within a pair of Bluetooth headphones. Confirm that a product meets requirements outlined in a standard, such as a maximum gain requirement for an over-the-counter hearing aid. To confirm production units meet required specifications. For validation and quality assurance purposes, as well as for the purpose of support and service to ensure repaired or refurbished products perform to their original specifications. Many kinds of measurements exist for these and for other purposes. However, the Big Six measurements are six that have historically been useful in these and in a wide array of applications. The first of the Big Six measurements, level, is one of the most fundamental audio measurements that you can make. As was just discussed, level, also known as amplitude, describes how big a signal is. The greater the amplitude of the signal, the higher the level. A level measurement answers questions such as, how much energy does our device output? What level can it output before it distorts the signal? A level measurement can be of an acoustic sound pressure level, or SPL, an analog voltage, or V, or a digital level in terms of digital full scale, or FS. Additionally, level can be represented as the instantaneous level at a particular moment in time. This is often used in waveform analysis to understand the behavior of an audio signal over time. Level can be shown as the RMS, or root mean square, of a sample period, which is a type of average. It can be displayed as a peak level, which measures the maximum instantaneous level that occurs within a given period. Looking at peak levels can be critical for avoiding signal clipping and other overload conditions. And lastly, level can be indicated as a peak-to-peak level. Peak-to-peak level measures the total voltage swing of an audio signal and is the difference between the maximum positive and the maximum negative peak. There are definitely other ways to indicate level. However, these are some of the most common. The RMS, or root mean square level of the signal, is the preferred method for most level measurements. This is because it can provide an accurate representation of a signal's effective power. This is achieved by squaring the instantaneous levels measured within a period of time, taking the mean of the squared values, then taking the square root of the mean. And as you'll recall, instantaneous levels can either be positive or negative. So squaring the instantaneous levels eliminates all of the negative values, which allows you to compute an average that is representative of the total energy of the signal. In addition, sound pressure level measurements are often A-weighted, which is a way of filtering the signal to mimic the frequency-dependent sensitivity of the ear. These kinds of measurements are typically indicated in units of dBA or dBA weighted. RMS level measurements are useful in nearly every context where level measurements are made. However, a few examples include measuring the noise floor of a microphone, measuring the sensitivity of a loudspeaker driver, measurements of brake noise, and an interesting one I've encountered, measurement of beehive noise over several weeks to track hive activity. Level can also be expressed in several different units. In the analog domain, the most common are volts, watts, dBV, and dBu. Volts and watts are absolute units, but can be awkward when expressing large ranges of values. For this reason, engineers often like to use dB, short for decibel, because it's a logarithmic unit. And this allows large ranges to be expressed in simple numbers. Although dB by itself is just a ratio between two values, the dB in level measurements assumes a reference to a defined constant. For example, dBV is referenced to the volt, where 0 dBV equals 1 volt. Minus 6 dBV is 6 decibels less than 1 volt, or 0.5 volts. And minus 100 dBV is 100 dB down from 1 volt, or 0.00001 volts. So a good rule of thumb is that for every 6 dB of level, there's approximately double the voltage. In the acoustic domain, the most common units for level measurements are pascals, a unit of pressure, and dBSPL. dBSPL is typically referenced to 20 micropascals, the threshold of human hearing, with 0 dBSPL representing the quietest audible sound. Last of all, digital levels are typically shown in FS or dBFS, with dBFS representing the dB level relative to digital full scale. With all of Audio Precision's APX analyzers, it's possible to switch between all of these units easily. The second of the big six measurements is frequency response. Frequency response measures the output levels of a device at different frequencies. Results are typically displayed in a graph showing level versus frequency. Because frequency response is essentially just a series of level measurements made at different frequencies, the units are the same as for level, with volts RMS, dBV, and dBSPL being the most common. Frequency response measurements can be made by several different methods. The traditional method being a stepped sweep of a sine wave from the lowest frequency in a range to the highest, with the output level of the DUT plotted on a graph at each frequency. The simplest of all frequency response measurements can consist of only 2 or 3 tones, with tones near the lower extreme, middle, and higher extreme of the range of the device under test. In addition to the step sweep, frequency response can also be measured using a multitone, which stimulates the device under test with several different tones simultaneously. And while the multitone does not seem to be used as frequently these days, it can still be useful in certain situations. For example, when testing devices that don't pass through pure sine waves due to noise or hum cancellation that's built into the device. You can also use a logarithmically swept sine wave, sometimes known as the chirp stimulus. Using a chirp allows you to produce a frequency response with many thousands of points of resolution in less than a second. It's much faster than the stepped sine sweep, and this is especially useful in contexts where speed is critical, such as production tests. In newer versions of AP's APX measurement software, a new stimulus type called fast sweep is also available. And fast sweep has a total sweep time that rivals the chirp, so it's really fast, while still allowing precise control of the discrete tones that are used in the sweep, making it much more akin to a traditional step sine sweep. All of these methods require a sine wave generator capable of producing the stimulus at equal levels across the desired frequency range. So why use sine waves? The sine wave is the only waveform with all of its energy at a single frequency. This phenomenon allows you to probe how much a device responds to specific frequencies and helps prevent harmonic distortion or other nonlinear characteristics of a device from affecting the measurement results. Typically, a frequency response measurement is made over the range of 20 Hertz to 20 kilohertz, since humans are only sensitive to sounds within this range. That said, there are also some high-definition audio applications and other edge cases where measurement to a higher bandwidth, such as 45 or 90 kilohertz, may be desirable. Frequency response measurements are typically normalized to show the difference from the level at 1 kilohertz, rather than the absolute sound pressure level, voltage, or digital level. With a normalized response, it's much easier to see how much the output level of a device deviates within a frequency range. This deviation can then easily be indicated as plus or minus X dB from 20 Hertz to 20 kilohertz or a different frequency range, and also with the inclusion of a graph if desired. Oftentimes, when we're looking at frequency response, we're looking to see if the response is flat. In other words, that the device responds with the same level across its bandwidth. However, sometimes we're looking for a characteristic curve that is not flat. For example, you might be looking at the maximum amplitude of an equalizer section, or you could be confirming that a weighting filter or other filter has been properly implemented. In the context of acoustics, that's especially true since a flat response in a speaker or a microphone is not necessarily the most pleasing to the ear. And what is pleasing to the ear is highly subjective and depends on the preferences of the listener. Floyd Toole, a pioneer in the field of acoustics, has said that frequency response is the single most important aspect of the performance of any audio device. If it's wrong, nothing else matters. Signal-to-noise ratio, or SNR, is a measurement that describes how much noise is in the output of a device in relation to the signal level. Every device has some amount of noise at its output. So the question is, how much noise is too much? The answer? It's all relative. A small amount of noise may not be objectionable if the output signal is very strong. In many cases, the noise may not be audible at all. But if the signal level is very small, even a low noise level can have an adverse effect. So to make the determination objectively, we need to look at the relative strengths of the output signal and the noise level, or to put it another way, the signal-to-noise ratio. SNR is actually two-level measurements. First, we measure the output level of the device with no input signal. This is the noise. Then we apply a signal to the device, typically a sine wave, and take a second level measurement. The output level is then divided by the noise level to produce the SNR reading. Typically, SNR is an expression of the largest signal a device can reproduce to the noise floor of the device. However, SNR is not very well defined, and it can also be made at other levels, such as the nominal level or operating level of the device under test. A quick word about units. SNR measurements are usually expressed in decibels. Using dB, a log unit, like level measurements, it makes it much easier to manage the large range in numbers. The kind of range that you can get when dealing with microvolts of noise compared to potentially 100 volts or more with power amps. Most noise sources are broadband, meaning that the noise extends across a wide frequency range. This means that a noise measurement of a device made across a wide frequency range will measure more noise than a measurement across a more narrow range. Bandpass filtering and weighting are often used with noise measurements to ensure that the measurements are both appropriate and comparable. Bandpass filtering limits both the low and high frequency range being measured, defining a measurement bandpass. A typical measurement bandpass for audio devices is 20 hertz to 20 kilohertz. A weighting filter may also be used, either alone or in conjunction with the bandpass filter. Weighting filters apply one of a number of standard weighting equalization curves, typically representing the response of human hearing. Importantly, any filtering used in a noise measurement must be stated as a component of the measurement condition. Now I will pass the presentation over to my colleague, David.
Thanks, Ben. With that, we'll go ahead and move on to the fourth of our big six measurements, total harmonic distortion plus noise. Total harmonic distortion, THD, specifically quantifies the distortion introduced by a device or a system by considering only the harmonic components of the output signal. It measures the presence of harmonics, which are the multiples of the fundamental frequency that are not present in the original output signal. This graph shows the fundamental, F, with the individual harmonic components beyond that fundamental. When a nonlinear device is presented with a given signal, the output of that signal consists of the original fundamental, the sum of all the harmonic distortion present within that signal, and noise. This brings us to the big six measurement of THD plus N, which accounts for both harmonic distortion and the additional noise introduced by the device or the system, which are present in the output signal. This graph displays the THD plus N level throughout the designated frequency spectrum, as opposed to THD, which applies only to the harmonics. By considering both harmonic distortion and noise, THD plus N provides a more complete picture of the overall audio performance and helps in evaluating the suitability of audio equipment for high-quality sound reproduction. This is what makes THD plus N one of our big six measurements, and not just THD alone. The analysis of THD plus N is performed by removing the fundamental frequency with a notch filter, then measuring everything else remaining. These are things such as harmonics, wideband noise, hum, other interfering signals. Bandwidth must be specified for the THD plus N measurements. For example, you would need to specify that you are looking for THD plus N with the bandwidth encompassing the audio range from 20 Hz to 20 kHz, or a specified band that is causing your device issues, such as the second through the fifth harmonics. Noise, of course, adds unwanted sound. This first graph shows the fundamental with the harmonics, and here we see the harmonics and the noise in between them much more clearly. THD plus N is measured by comparing the output of the device under test to the original input signal, then quantifying any added harmonic distortion or noise. THD is typically expressed as a percentage and represents the ratio of the RMS value of the harmonics to the RMS value of the fundamental signal. Lower values are generally better. Typically, a lower THD plus N percentage indicates a lower level of combined distortion and noise in the output signal. This suggests better audio quality and fidelity. It's typically desirable to have THD plus N values as low as possible. There are some applications wherein a certain level of distortion may be desired, such as outboard effects processing, like a guitar distortion pedal. While high THD plus in can result in audible distortion within the audio signal, this distortion can add artifacts that were not present in the original signal, degrading the clarity, accuracy, and overall fidelity of the audio reproduction. Higher THD plus in levels can also be representative of a loss of audio resolution, which in turn may obscure details such as rapid transient response in the audio signal. Dynamic range may be compressed as well by way of increasing the noise floor. It can also affect the frequency response of the audio system, particularly in the presence of nonlinear distortion components. It may introduce frequency-dependent changes or irregularities, causing variations in the perceived tonal balance of the sound. THD plus in can impact the stereo imaging and spatial representation of the audio. It can cause inaccuracies of the localization and placement of sound sources within the stereo field, resulting in a less defined stereo or multi-channel image. Heading into our fifth measurement, phase. Phase is defined as a relationship in time between two or more signals at a given frequency. Qualitative analysis of phase is required when evaluating more than one channel concurrently, such as a stereo, headphones, surround sound home theater systems, car audio, and multi-input devices. In a sine wave, the phase is typically represented as an angle or a fraction of a cycle. At any given point in time, the phase value indicates its position of the waveform within its cycle. For example, at the start of the cycle, the phase is 0 degrees, and as time progresses, the phase increases until it completes one full cycle, 360 degrees. Phase can also be represented in terms of delay or time shift. When comparing two signals, the phase difference can be expressed as the amount of time one signal lags or leads the other. This time difference can be measured in milliseconds. We can understand phase in two different states, relative and absolute. Relative phase is the phase between multiple signals at a specific point in time. You can see in this figure that the phase between the speakers is flipped, and thus the relative phase at the output is reversed. Absolute phase is the phase difference from input to output. In the second figure, you can see that although the relative phase between the speakers is matched, the absolute phase from input to output is reversed. In an ideal situation, of course, depending on the functionality you're looking to achieve, both the absolute and relative phase of your intended signal is matched. The effects of interchannel phase can be perceived in the following ways. This is by no means a complete description. While the effect of phase being off by one sample may be imperceptible, it can hinder serial processing. In this case, drift may also occur, changing phase alignment over time. When a speaker produces two sine waves of the same frequency perfectly out of phase, this pure reversed polarity will produce no sound. Electrically, the waves cancel each other out and become zero. Acoustically, however, one would need to account for the input delay of source to microphone, as well as any delay between multiple speakers. In this case, a reversed polarity will make a noticeable difference in tonal quality, timbre, and perceived pressure. This is known as destructive interference. In the same fashion, when two signals in perfect phase alignment, they will double in amplitude, exciting these frequencies that align. This is known as constructive interference. In this animation, channel A in green and channel B in blue are reproducing the same sine wave. For example, 1 kilohertz. As channel A and channel B shift in phase, the output amplitude, in red, changes. When both signals are perfectly in phase, the amplitude is doubled. When both signals are perfectly inversed in phase, they cancel out. The result of that signal is 0. This brings us to our final topic in our Big 6 measurements, crosstalk. Crosstalk refers to the unwanted interference or bleeding of signals between 2 or more channels. It occurs when the EM field of one channel influences adjacent channels, causing an undesired mixing of signals. In this image, we can see an analog example of crosstalk. For example, as a signal is fed into input 1, the expected output should come only on output 1. Due to any number of design choices, shielding, circuit design, cable proximity, crosstalk has permitted bleed of the signal into output 2. In digital applications, crosstalk can happen when multiple signals are processed or transmitted simultaneously via one or more data transmission lines. Again, physical design and cabling play a big part in this. This graph shows 2 separate crosstalk results using the one-channel undriven measurement within the APX 500 software. This measurement is performed by injecting signal onto one channel while no signal is present on the other, then measuring the output of the unintended recipient of the signal. This is called one-channel undriven, as one channel has an injected signal and is considered driven, and the other does not. The crosstalk from channel A to channel B is shown in red, while the crosstalk from channel B to channel A is shown in blue. You'll notice that beneath the larger spikes at 10 and 11 kilohertz respectively, you'll find a smaller spike of the opposing channel. This is the result of the crosstalk being driven onto the undriven channel. When grounding is not implemented correctly, crosstalk can occur as a result of shared ground paths, commonly known as ground loops. A ground loop forms when there are multiple paths for current flow between different components, creating a circulating current. Crosstalk is considered one of the Big 6 because it directly relates to the performance of devices and their ability to maintain channel separation. As signal bleed between channels is increased, stereo or spatial imaging is significantly impacted. This is particularly problematic if the data being transmitted must be serially reproduced, as in the case of most digital transmission. In audio applications, this can also hamper transient response on the affected channel, further impacting processes such as compression or gain structure. In both digital and analog systems, unwanted noise and artifacts can appear, as unwanted signal or data shows up where it's not expected. Crosstalk can introduce frequency-dependent interference, and in conjunction with the phase issues I touched on earlier, this can cause an exaggeration or attenuation of certain frequencies across the spectrum. This could lead to an inaccurate equalization of a single component or the system as a whole. In some cases, crosstalk can affect low-level signals with a high dynamic range. The impact of detectable crosstalk becomes more significant as the level of the initial signal decreases. For example, if your introduced signal is 2 millivolts RMS, and if crosstalk is detected up to 1 millivolt, then the impact of that crosstalk effect would be detected starting at 50% of signal power. Let's consider then, if the device picks up crosstalk up to 1 millivolt, And if your introduced signal is 1 volt RMS, then a 1 millivolt crosstalk signal will not have much effect overall. This same concept applies to high dynamic range signals, especially at low levels. These measurements, level, frequency response, signal to noise ratio, total harmonic distortion and noise, phase, and crosstalk, constitute what we at Audio Precision and Axiometric Solutions consider the Big Six measurements. In conclusion, we'll recall that sound is caused by vibration and can be represented in a device by an electrical or digital signal that is analogous to pressure fluctuations in the air. Historically, the Big Six measurements have been fundamental ways to objectively quantify the performance of an audio device. These 6 measurements are still relevant today and useful across a wide array of applications. Audio Precision's APX 500 measurement platform can perform all of these measurements and many more. You can contact us at the technical support team with any questions that you may have. Which brings us to our questions. I'll go ahead and ask Ben this question that we have coming in. Can you elaborate on why a flat response might not always be the best for speakers or microphones?
Great, thanks, David. So a flat frequency response in speakers or microphones means that all of the frequencies are reproduced at the same level, which might seem ideal for accurate sound reproduction, but that's not necessarily what's most pleasing to the ear due to the way that we perceive sounds, which is not linear and is influenced by many factors like room acoustics, listening volume, and personal preferences. So, for instance, speakers might be designed with a slight boost in the bass or treble frequencies to accommodate for the ways that humans perceive sound at different volumes. Well, similarly, microphones might have tailored frequency responses for certain applications, like a vocal mic boosting certain frequencies to help voices cut through the mix. So while measurements help us to understand the technical capabilities of these devices, the ultimate judgment often includes some context-specific considerations. In production testing, this is why golden unit or target curves are often used. A golden unit is a device that has the optimal or target frequency response for a particular product type or model. And it's used as the reference point for all of the units that are produced for that model. So instead of aiming for a flat response, devices are tested and adjusted to match the response of the golden unit, which ensures consistent sound quality across all units. Second question that we have here, what are some reasons you might measure instantaneous level instead of RMS level? There's a number of different reasons to use either of these, but one reason to measure instantaneous level is that it gives you a more accurate picture of an audio signal's moment-to-moment changes, which are crucial for understanding the transient response of a device. And transients are fast, short duration peaks in an audio signal, like a snare hit, something really brief. And they can play a significant role in our perception of sound. Another reason you might want to measure instantaneous level might be for digital systems, where it's important that the level doesn't exceed the hard limit of 0 dBFS or 1FS full scale, because any signal that exceeds the limit will clip and produce distortion. So yeah, that's a couple examples.
Thanks. Here's another interesting one. High def audio doesn't increase human hearing beyond 20 kilohertz. So why would we measure higher? That's a pretty good question. You're very correct that high def audio does not really go beyond 20 kilohertz, but what we consider the audio range is specifically the range of frequencies that are in human hearing. There are certainly other applications that go beyond 20 kilohertz. We can think of it in terms of vibrations. So mechanical vibration in machines or other types of operated infrastructure. If you have a sensitive enough equipment to measure it and you are worried about a point of failure, you can monitor those vibrations and analyze them to see things such as at what point certain frequencies would have a resonation effect within it. We've seen various things come in, as Ben alluded to at the beginning, about the buzzing of bees. While it can be heard, and it certainly is part of the 20 kilohertz, there are other aspects to it that are beyond the range of human hearing.
Another question that we have, what is the origin of the units dBV and dBu? Where do they come from? Both dBu and dBV are units that originated from the decibel. And the decibel is 1/10 of a bell, a unit which was named after Alexander Graham Bell, who was a pioneer in the field of telecommunications. dBu stands for dB unloaded, and it has its origins in the early days of telephony, where power and impedance matching were a more significant concern. The voltage that corresponds to 0 dBu is about 0.775 volts RMS. And that number isn't arbitrary. It's the voltage that produces 1 milliwatt of power across a 600 ohm load, which used to be the standard impedance for telephone lines. So because impedance matching is no longer as much of a concern these days, it can actually be more convenient to use dBV than dBu, because it's much simpler to relate signal levels to 1 volt, which is the reference for dBV, than it is to relate them to 0.775 volts. So this is actually, I think, the reason dBV was created, for easier interpretation of measurements. So both of these units are used to measure audio levels in a logarithmic scale, and they allow for easier comparison of signal levels across different equipment, different systems.
Thanks. I have another question here. When making THD measurements, what should be the bandwidth? That's a very subjective question. It depends on the application to which you're looking to measure your THD. It depends on issues that may have arisen that you're trying to locate. You can set your bandwidth for the entire audio spectrum if that is what you're looking to reproduce, and you're concerned about any types of distortion noise that takes place within that range. Or as I alluded to earlier, you know you're picking up something in, say, the 5 kilohertz range, and you put in a signal at 1 kilohertz, well, you can select the set of harmonics that encompass that 5 kilohertz range in which you're looking to fix. So again, the set bandwidth isn't necessarily a perfect answer. It is entirely dependent upon the application and the type of measurement that you're looking to take.
Mm-hmm. The question here just came in. What all measurements in the Big Six can be measured in open loop? To think about this, but open loop is as opposed to closed loop, which is where you have a closed system where your audio analyzer is both driving the stimulus into the device under test and measuring the output of the device under test in one operation. Open loop might be, say, a smartphone where you have to place a file onto the phone and play it in order to get the signal out of it. There's no way to loop the signal through. So what measurements in Big 6 can be measured in open loop? Well, thinking about the phone here, level you can certainly make because, first of all, you're not always generating any stimulus when you're making a level measurement. Sometimes you're just measuring noise. So you can certainly measure level open loop. Frequency response, you can also measure open loop in the context of a phone, just because it's helpful to have a particular context in mind. You can put a sweep file, say a WAV file or MP3 file on the phone and play that file while starting the acquisition on your analyzer. And that allows you to still measure the frequency response, say, of a headphone output on the phone. Signal to noise ratio, that one can be trickier because it involves two level measurements. So, with the APX measurement platform in a closed loop scenario, it's very easy to make a signal to noise ratio measurement. You just click start and it automatically makes the two different measurements, one of noise, one with the signal level, and then computes the ratio and plots it. But open loop, you can still do it, but you have to make the individual level measurements and then compute the ratio from those. So there's just a couple extra steps, but it can still be done. I think, yeah, total harmonic distortion, phase, all of these things really can be measured. Crosstalk, all of these things can be measured open loop, actually. So yeah, I'm pretty sure all of them can be measured both closed loop and open loop.
All right, here's one. Can speech quality be considered part of the Big 6 as well? I think this is a really interesting question because speech quality can be defined in terms of the Big 6. You're looking at very specific frequency response ranges. You're looking at specific levels. You're looking at removing distortion and noise that is not in the tonal speech realm. That is, I think speech quality in and of itself wouldn't necessarily be considered part of the Big 6, but that is something that you would be able to determine using these Big 6 measurements.
So we had a question on whether it's possible to simulate our APX 500 measurement application. I assume for purposes of just taking a look at how the measurements are performed. And the answer is yes. Anyone can download the software from our website, and actually it might be a great idea if you're interested in just poking around with these different measurements and learning more. If you go to ap.com and go to the software downloads page, you can download our measurement software and run it in what we call demo mode, which, you're not measuring a real device, of course, but there's a way of putting it in an ASIO loopback mode that allows you to actually generate and measure, real signals in a sort of loopback configuration. So if that's something you're interested in, definitely, and you want help with that, feel free to contact us at support using the contact information we provided earlier. You all should have access to a copy of the slides after this webinar. see what else we have coming in here. Does APX test distortion with a multi-tone stimulus signal? Yes, we do. With multi-tone, I believe it's called, instead of total harmonic distortion plus noise, it's total distortion plus noise. And I think part of the reason for that is you have multiple tones going at once rather than just one tone, so you have to be selective at what frequencies you measure the harmonic distortion. So yes, it is possible. Another question, is there a good way to measure audio delay through a system? Yeah, so if you use an APX analyzer, those are delay calibrated, meaning a delay measurement doesn't include any delay inside of the APX analyzer itself. So we have a measurement called delay, and when you run it, basically you output a stimulus into your device that you're testing, and you output the signal that's output from the device comes back into the analyzer, and you press start, and it measures the time delay between the signal going out and the signal coming back in, and it shows you that delay is a single number per channel if you have multiple channels.
And I think we're going to conclude the question portion right now. Is that okay with you, Ben?
Yeah, that's fine.
Perfect. Well, thank you, Ben and David, for your excellent presentation, and thank you to our audience for your participation today. An on-demand version of today's presentation will be sent to the email that you registered with. You will still be able to ask questions through the question module in the on-demand platform, and we will follow up after with email. Also, be sure to register for our upcoming webinar, Audio Testing in Smart Devices, that will also be included in the follow-up email. To the questions that we were not able to answer today, we will follow up via email within the next few days. We hope you have a great rest of your day, and we look forward to next time.
Thanks, Amanda. Take care, everyone.
Yeah, thank you for coming.